Hello everyone, my name is Robel Lemma. I would like to thank Professor Salib for giving us this opportunity to present our Capstone projects. It's been a challenging but rewarding journey. This presentation is a part of my work for Data 670, and I will be walking you through the progress and goals of my project, which explores how flight disruptions and safety events evolved during COVID-19 timeline. The goal is to uncover insights that can help airlines and regulators respond more effectively during periods of operational stress. This slide gives you a snapshot of the project before we get into the details. I'm analyzing how did airline reliability, meaning delays and cancellations and safety events reported by the FAA, evolved over time, especially across the COVID-19 period. To explore this, I'm using two large public datasets from the BTS and FAA, which will clean and align by quarter. This project combines descriptive analysis, looking at cancellation rates and delay causes, with a predictive model that aims to forecast flight cancellation before they happen. Yes, the ultimate goal is to help both regulators and airlines make proactive decisions when disruption arises. Now let's define what's actually included in this project. This study focuses on a 5-year period from the first quarter of 2019 through the first quarter of 2024 to cover US commercial aviation performance before, during, and after the peak of the pandemic. The scope includes quarters where both datasets were consistent and reliable, allowing for valid comparisons. Unique quarterly alignment, I will be able to describe seasonal trends, test for correlations, and build a cancellation prediction model with a well-labeled and integrated dataset. So everything going forward reflects this clean and controlled slice of time. Now let's talk about the problem this project is trying to solve by asking a question. So why this topic? We know that COVID caused major disruptions in the airline industry, not just in flight schedules, but possibly in safety outcomes too. Most studies focus on either delays or incidents separately, but not how the two might be connected. This project explores whether operational stress like widespread delays align with increase in safety reports. By looking at both sides together, I hope to uncover trends that can guide early intervention and improve both safety and reliability going forward. Let's now talk about why this problem matters to the aviation industry. Reliability and safety are the two pillars that keep commercial aviation running smoothly and keep passengers confident about flying. At the same time, every mechanical issue, delay, or disruption must be tracked and reported to regulators like the FAA and the DOT. These agencies monitor trends and ensure that airlines are staying within safety thresholds. The COVID-19 pandemic didn't just delay flights, it threw the entire system into shock. Fleets were grounded, staffing levels dropped, and delays piled up. But what was not clear is how those disruptions affected safety reporting and risk. This project aimed to strengthen that decision making with evidence from the real patterns. Okay, now let's take a quick look at the key player involved, both the data providers and the people who rely on this analysis. First, the data comes from the two federal agencies. As I said, the Bureau of Transportation Statistics, which applies flight level operational data, and the FAA, which reports safety events across the US airspace system. On the stakeholder side, airlines use this information to manage crew schedules, reduce delays, and prioritize maintenance. Regulators like the FAA and the DOT rely on trends to adjust oversight and inspections. Insurers and investors watch these indicators to assess risk exposure. Passengers, cargo companies, and airport teams make time-critical decisions based on their airline reliability, affecting bookings, shipments, and gate logistics. And finally, researchers and advocacy groups use these datasets to study patterns, shape policy recommendations, or advocate for systemic reforms. This project aims to bring this fragmented perspective together, offering a clearer quarter-level view of how operational and safety interact, especially under stress. Let's now talk about the business objectives guiding this project. The first objective is quantify operational reliability trends, is to analyze trends in cancellations and safety incidents across different pandemic phases. This means I'm not just counting delays, I'm trying to see if safety risk also increases when the system is under stress, like in the second quarter of 2020. The second objective is correlate delays with safety incidents, just to uncover correlation between delay causes, like weather or air traffic control, and FAA-reported incidents. For example, are safety issue more likely when weather delays spike? This could help airlines understand which types of disruptions are most risky. The third objective is build predictive cancellation model that can identify cancellation risk before it happens. If you know that a flight from LAX to JFK, New York has an 80% chance of being cancelled tomorrow, the airline can reassign crews, rebook passengers early, and avoid last-minute chaos. Together, these objectives aim to support better decision-making in airline operations and federal oversight. Let's talk about how I will define success for this project overall. First, the dataset needs to be clean, complete, and high quality. I'm targeting less than 0.5% missing data across the key fields. If the foundation is shaky, as you know, everything that follows could be compromised. Second, the predictive model should perform well, especially I'm aiming for an AUC of at least 0.8 and an F1 score of 0.75 or higher. These thresholds help ensure the model is both accurate and reliable for real-world use. Third, the final deliveries should be usable and reproducible. That means clear KPI dashboards, clean code, and transparent documentation so others can understand and even extend this work. Altogether, success is not just about one model score, it's about the quality of the full workflow. Let's take a moment to talk about the research context behind this project. Many previous studies have explored either airline delays or aviation safety incidents, but almost always in isolation. Delay prediction models using BTS data are common, and the FAA incident summaries are often used in safety trend reports. However, linking these two areas, reliability and safety, has been difficult. Even DOT audit reports have pointed out data integration challenges between BTS and the FAA sources, especially due to differences in structure and scope. What's missing is unified analysis that examines both operational and safety patterns together across multiple phases of disruptions. So this project addresses that gap by aligning FAA and BTS data across pre-COVID, mid-COVID, and post-COVID quarters, allowing us to examine whether operational breakdowns align with spikes and report safety incidents. Now let's dive into the specific key performance indicators, KPI, I will be tracking throughout the project. This KPIs table serves two purposes. They will guide the descriptive analysis in the first half of the project. Then they will also help evaluate model performance in the second half. The first KPI is the cancellation rate by quarter. I will monitor for any increase greater than 30% compared to the pre-COVID baseline in the first quarter of 2019. That would suggest a significant rise in operational stress. And the second KPI tracks delay minutes by cause, which has special focus on late aircraft delays. If those exceed 10 minutes per flight on average, that could point to problems in turnaround efficiency or scheduling breakdowns. The third KPI which I focus on is FAA incident rates, specifically the number of reported incidents per 10,000 flights. If this crosses 1.5, it may indicate emerging safety risk, especially during turbulent recovery phases. The fourth KPI comes into play during modeling. I have set minimum threshold for precision, recall, F1 score, and AUC. all of which I plan to evaluate in week 8, maybe. So this will help determine whether the cancellation classifier is accurate and useful for early warning decision making. Altogether, these KPIs bring structure and accountability to the analysis, making it easier to communicate results and help decision makers interpret their finding with confidence. This slide summarizes what has been completed so far and what have been learned along the way. In week 1, I finalized the project topic and narrowed the focus to US aviation during the COVID-19 period. That early clarity made it easier to connect the research questions to the real-world needs. In week 2, I reviewed two key datasets, the BTS on-time performance data and the FAA incident reports. I realized it's not just about finding relevant data, it's also about understanding its shape, gaps, and limitations. In week 3, my focus is on profiling the variables. I examined field structures, coverage periods, and consistency, which helped me think ahead about modeling strategy and data prep. And in week 4, I created a high-level diagram and aligned both datasets by quarter. That helped clarify how records relate across sources and made future joins more straightforward. Overall, each stage has brought both progress and insights, especially about how data preparation choices affecting everything that follows. So this slide provides a quick overview of the two datasets and how they have been structured to support both analysis and modeling. The first dataset comes from the Bureau of Transportation Statistics, like I said, with over 7.6 million flight records across 26 variables from 2019 to 2024. It includes details like flight dates, delays, and cancellations. And the second dataset is from the FAA, Federal Aviation Administration, and contain about 23,000 validated incident reports spanning 2015 through the early 2025. This report covers everything from minor ground events to serious in-flight issues. So to bring the two datasets together, I created a shared quarter level field. This lets me aggregate trends by time without inflating the join, which keeps the structure clean and efficient. And these key fields driving the analysis includes the flight date, the departure delay, and the cancel. That last one, the canceled, is the target variable for my modeling. And it's highly imbalanced. Only 3.3% of the record represent actual cancellations, which means I will need to adjust for that during the training period of the model. Together, these structured and aligned datasets from the foundation of the descriptive KPIs and predictive modeling I will present in the next stages. Now, here is my high-level view of how I plan to bring the two datasets together. By the way, this is not a relational database, so I won't be using primary or foreign key joins. Instead, I will be using a shared time based key called quarter label to align both datasets, one from the BTS and the other from the FAA. On the left, the BTS table includes flight level records, things like departure delay, carrier delay, and the cancelled flag, which is my target variable, which will be later become the target for predicting modeling. On the right, the FAA table contains safety incident data that includes incident date, aircraft info, and a simplified injury count, which I will compute by combining multiple injury fields. So the goal is just to summarize FAA incidents by quarter and merge that context back into the BTS flight level data. That way, I will be able to compare delay trends with safety event trends, even though the two datasets do not match row for row. Later in the data preparation phase, I will complete the aggregation, clean both sides for consistency, and validate the quarter label mappings. Looking ahead, the next major milestone is the start of data preparation and cleaning. This will involve handling null values, Coursing data types where needed and creating new variables like delay indicators or aggregate incident count. Once that's complete, I will move into the data understanding and visualization. Here, I will use descriptive plots to explore trends over time, compare delay and incident patterns, and run quality checks to confirm everything looks consistent. After that, I will transition into modeling and evaluation. The plan is just to test multiple classifiers like logistic regression, random forest, and gradient boosting, and compare their performance using metrics such as precision, recall, and AUC. So this full pipeline will help validate whether operational stress indicators can predict cancellations and whether there are any useful alignment with FAA safety data over the pandemic timeline. So I'm using these references during my project, and thank you for your attention. Now I would like to open the floor for any question, comments, or feedback. Thank you very much.